Okay, next one, spherical area and volume. It is a very, very important for our various calculation. Okay, why don't we consider a point inside the circle of radius capital R? We know a point, there is a circle of radius capital R. Then we choose a small circle of a radius small r. And we have angle theta measured from the x-axis counterclockwise. So any point inside this circle is represented by this. And theta runs from 0 to 2 pi, and small r runs from 0 to r, capital R. Okay, what is the displacement of the point inside the circle? I'd like to introduce a small displacement from this a certain point to another. And we will find there is a shift in the angle, the theta, and there is shift in the radius, that is the r. And as soon as we use the differential form, the theta or the r, we take the limit as the delta theta goes to 0, and we take the limit as the delta r goes to 0. So we neglect any additional p's. There's a higher order piece is neglected. All right, why don't we find the unit vector along the theta and radius direction? The radial direction unit vector is defined by the radial displacement. This is a partial derivative of the position vector with respect to the radius only. This means we have kept the theta equals constant. And divide this one by its own magnitude. Therefore, the unit radial vector's magnitude is 1. It is in a similar manner, unit tangent vector. Tangent means you have a circle, you have a radius, it is a radial vector, and a tangent to a circle is only, it touches a circle only at a single point, and middle school students know that they are making a right angle. So ER and E theta, they must be perpendicular to each other. However, we can find it explicitly. How can I do that? Vary x with respect to theta only and keep radius constant. So, because I know what x is, we take the partial derivative with respect to r. This guy is a trivial, and we are left with unit radial vector because square sum, its magnitude is 1. So this guy is identical to this, and what's that? That is that. And what is the direction? This is a unit radial vector. Finally, you will find these two are perpendicular to each other. These coordinates are exchanged, and a single one has negative sign. We can find this unit vector, even high school student can find this unit vector that is perpendicular to the ER. However, we can compute by hand, take the partial derivative with respect to angle of the displacement vector. This theta, okay, replaced with minus sign, and this one is a cosine. Now we know this one has a unit magnitude, this one has a radius r. So magnitude of this vector is r. Dividing this by this one by the magnitude r, what we obtained is a unit tangent vector. As we already have tested, ER and E theta, they are perpendicular, so the scalar product must be 0. They are unit vectors, so square and E theta squared, they are both 1. Okay, we are ready to compute the area spanned by the these two sides, what dr er hat and r d theta e theta hat. And we know everywhere at every point er and e theta they are making a right angle. So that means it is a rectangle. And we can compute the cross product, and cross product must be proportional to the z-axis. So this triple scalar product will give the area of this rectangle. Finally, rectangle's area is trivial. And we know RdR, that is simply expressed in this way. So this is nothing but the differential of 1/2 r squared. Therefore, combining everything all together into a single piece and integrate over the region from radius 0 to capital R and the angle 0 to full angle for 2 pi, the answer is pi r squared. Next, we consider a sphere. In sphere, we have a spherical polar coordinate, and z-axis here. We have a radius r. This is a sphere, and we have a cone. Its apex angle is 2 theta. So this angle from the z-axis is called the polar angle theta. Polar angle. The z component is this, because this is a right triangle. We have radius, and what's that? This is r sine theta. And this right triangle shows that the radius from the z-axis, that is r perp, is called r sine theta. However, r perp, this is a kind of lever arm, and it rotates freely about a 2 pi angle. That angle is called azimuthal angle. Azimuthal angle. Therefore, the general form of any directional unit vector is z component is cosine, and x and y are dependent on sine, and x component is multiplied by cosine phi and sine phi. Remember, this polar angle runs from 0 to pi only, and the phi runs from 0 to 2 pi. They are different. Azimuthal angle and polar angle, they are different. Okay, using this unit radial vector, I can always express the arbitrary point on a sphere in this form with the radius r. The calculation of the displacement, infinitesimal displacement vector on a sphere in three-dimensional space is composed of a radial and a unit vector along the direction of increasing polar angle and azimuthal angle. You will find these are you can compute using this expression or of them explicitly. Before evaluating those values, we will find if you rotate along the polar angle radius, and if you have an angle delta theta, and what is the arc length? This arc length is, because this is a circle of radius r, arc length is r delta theta. In the infinitesimal direction, it is limit, we have r d theta, that is the infinitesimal arc length due to the rotation of the polar angle. What is this? This is the displacement along the radial direction. So from the radius r and to r plus dr, the radial direction has the unit radial vector multiplied by the differential dr. What about this? This is azimuthal direction because this is r perp and azimuthal angle rotates about the z-axis and the level arm is r perp, that is r sine theta. We know this height along the z-axis is r cosine theta. This is r sine theta. As a result, oh, there is a typo. This is not d theta. It should be d phi. Okay. Finally, x vector, its radius derivative is unit radial vector. And square, 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 sum is always 1. That's it. If you take the derivative with respect to the polar angle, you change this. So sine becomes cosine, sine becomes cosine, cosine becomes minus sine. And again, square, square, square sum is r. So magnitude of this is r. Dividing this one with by this magnitude, you will find the unit vector along the angle theta. This. So just pull out this contribution. So this is the unit vector along the theta. If what happens if we consider phi? Phi dependence appears only on the xy axis. Z-axis independent of phi. Therefore, the unit vector along the phi direction is trivial. This is the magnitude, and after dividing this one by its magnitude, r sine theta, what we obtain is the unit vector along the phi direction. There is an explicit computation of the scalar product with the theta and phi. And theta and phi on the surface of a sphere, r is fixed. We have an angle d theta change, and along the azimuthal direction, d phi change. So this change will result in some angle, and we are interested in the area of this rectangular region in the infinitesimal limit. We know angle is d theta, and the arc length, this one is r d theta. And angle is d phi, but arc length is r sine theta d phi. Therefore, area of this rectangular region is this one multiplied by this. Therefore, r squared sine theta d phi. And sine theta d theta can be computed in a simple manner, but more convenient way is replace this one by d cosine theta, and let it this theta runs from 0 to pi, but at 0 cosine is 1 and this one is minus 1. So sine theta d theta integral can be done with from 0 to pi, but this one is equivalent to evaluate the integral from minus 1 to plus 1. So as a result, the area of a sphere of radius r can be expressed as an integral of this differential form. This radius r is fixed. I pull out the r square, and we carry out the angular integrals. And these angular integrals are decomposed into two pieces. Here r squared is missing, and this one is just 2, and this one is 2 pi. That's the reason why I usually have 4 pi r squared.